All right, thank you everyone for joining us today. We are very excited to have Control Techniques here, Kevin Manton, the American Director of Engineering here at EMC to help us with a joint webinar today on VFDs and power supplies. Before we begin, a few notes. This webinar is being recorded and we will send out a link to everyone who attended with the recording within a couple days. If you have any questions, you can chat at the bottom with myself and we'll make sure we get those sorted out. If you have any questions, you can ask those at any time at the bottom. We will save all those questions for a question and answer section at the end, but feel free to ask them at any time. Your audio will be muted through the presentation, but like I said, you can chat or ask questions. Otherwise, we'll go ahead and turn it over to Kevin with Control Techniques for today's presentation.
Oh, good morning, everyone. So I put a presentation together for you today to talk about VFDs and power supplies, mainly focusing on the two main ones, of course, the utility transformer and the generator. I split it into three sections. Just a brief, understanding about VFDs and power harmonics, why. This may have been covered on previous webinars before, but just a recap. And then the impact of harmonics and other equipment and remedial techniques. What I wanted to make clear on this, I'm looking more at the lower frequency spectrum and harmonics, yes, not EMC. So the areas I'm fully focused on are what's on the supply. Again, we can cover other areas later if needed on EMC, RFI, in that, below 30 megahertz, but with the harmonics today, it's usually covering those frequencies in the spectrum up to 3 kilohertz. Okay, and the second thing is I'm not going to go over DC drives and notching effects on that. Again, this can be handled separately. This is mainly focused on the VFD and static rectifiers. Okay, so I'm going to start off with some understanding of the VFD, and I thought I'd take a practical approach on this. Looking at it's probably an existing system today, which may be upgraded or wanted to be upgraded to come in line with variable speed. And typically, I've taken a pump. These are the type of applications where it gets affected with, when we talk about constant power, constant running apparatus or applications where the supply is important. On a fixed speed starter, I'm talking here, it could be across the line, it could be a soft starter, it could be an auto transformer, Korndorfer starter, etc. But typically, a pump regulated with a motorized valve, maybe to regulate the flow or pressure. And then the utility to support this application. In this case, I'm looking at 250 kilowatts on a 1 MVA transformer, for example. Should be adequately rated, for the starting. And then the pump's controlled with a motorized valve, etc. for the flow. Could be manual, you never know. And then on that supply, we've also got some other equipment, industrial equipment, the office, other apparatus, and maybe other motors and heaters, which are making up the process. The supply transformer, typically a delta star connection, where the star point is grounded. And then because it's a passive or inductive load, mainly with the motors, there may be some power factor correction equipment in there to get us up, from 0.8 to maybe 0.95, etc., to meet the utilities requirements. Okay, so this is a typical practical approach, as I said, where I'm going to go ahead now and think about trying to implement a VFD and what impact it may have on the system. And of course, if there's a pumping station, there's always got to be some backup. You have some redundancy, so that this is where the generator comes in. I've used larger powers here, 1 megawatt or mega MVA. These could be smaller, of course. It's all in respective powers. And at this stage, I just want to identify these two areas of connection, and typically known as the point of common coupling for power. So we've got a low voltage power point of or PCC, and as a medium PCC, medium voltage PCC, which is where everything else is connected to the equipment. I'm focusing on this pump. What else is connected to this pump on the LV, and what's on that system or that system point? What else is connected on to other services on the MB. All important points when we start considering including a VFD. So now here's my VFD. I picked a graphic which is a Control Techniques drive freestanding enclosure. And now, of course, prime purpose was to put the VFD in there to do some constant pressure control, and save some energy. Typical application for this, of course, whether it be usually discharge pressure or flow. And now we're thinking about, well, I'll put this in, what do I need to consider when I insert this device? Of course, again, laying the seeds probably for future things. Of course, the motor's got to be examined. You may switch at the motor because now we've got to have a variable speed range, of course, and also be able to cater with the PWM switching waveform with the dV by dt. So it's important that these existing motors, can they do them? Maybe if they're well oversized, they could, but usually they get changed out with the drive. Motor cables, important. People seem to forget these things. It's EMC, PWM waveforms, high switching frequency, high, very fast turn on times. It's a big emitter. It's a big, area of emitted waveforms. So shielding is important, even if it's running conduit, okay, just to keep that high frequency noise down. But by the by, that I'm not covering that today, but just these initial indicators, okay. And of course, when we look at the input, we got to start thinking about what's happening on there. And this is what I'm going to focus on next, is what currents has changed now when we insert this drive. And of course, cables, transformers, etc. They can typically increase in size because of this. PFC, again, is passive, is capacitor. A capacitor in a circuit with any frequency, any range, could be a potential resonant path. So I'm going to try and look at this. And also, when we put these variable speed drives on a VFD with a constant voltage source supply, a constant voltage source, the power factor is really good. So all of a sudden, maybe the power factor becomes redundant, or you need less impact and less kVARs to be considered, because what we don't want this system to do is start to go leading, of course, yes. So we're looking at that in some consideration, but the thing we need to really look at is what this drive is doing onto the to the mains when we connect it. We've got this wonderful back end where we're doing the variable speed, doing a nice constant pressure control. But what's going on the power supply side, and this is what I'm going to look into more detail now. Okay, so I'm trying to build up the picture and set the scene. So again, most of you, I hope, is familiar of the power schematic of the variable speed drive, the VFD. It's a typical rectifier front end, because it's constant voltage source. It's got a big DC link capacitor or capacitance, and the back end, which is IGBT for regulating your voltage and frequency for your motor. And of course, there's additional componentry in there. I'm not going to go into too much detail, but those are the three main fundamental power blocks to the drive. Okay. So, what do we get on that front end? This is what I'm more worried, more concerned about for this presentation. Is what does this diode rectifier with a capacitive load do? And if you dare enough to put a scope or a clip on it, meter on there, you will see the current is very peaky. Okay, it's not nice and sinusoidal, purely because of the diode rectification and with peak charging through the capacitor. Okay, and with the diagram to the left-hand side, you will see that how the diodes were commutating from phase to phase and produces this double peak each halfway sine wave of current. And these peaks can be very, very high. The limiting factor for this is the line impedance, the line choke. This limits the peak inrush. The more, of course, the more inductance you can get in there, the less peaks. But there comes up a time where it has less effect, and also it has impacts on the performance of the drive due to voltage drops, etc. But along with that, look at the voltage, how it starts to distort. It's not looking too nice, and that voltage is probably the most concerning thing when we talk about variable speed drives, or we call them nonlinear loads because the current is non-sinusoidal, which has impact on other equipment. And this is what I'll be mostly focusing on as you see as we go along this this presentation. Voltage is seen across all the equipment, okay, but it's a product of what's generated from the current drawn from the supply, okay. So again, you can see it's ugly. The more impedance we start adding to the line, the worse that voltage will get, okay. So simple overview of the front end, diode rectifier, three-phase bridge with a capacitor. And again, this is mainly on most VFDs today is a voltage source drive, okay. And of course, if we started looking at the line-to-line voltages with lots of inductance, you can see that the voltage peaks can start clipping and start squaring off. Now it's definitely not looking like a nice sinusoidal waveform. What impact does that have on other equipment? And what do we need to look out for, and how can we improve this? So these are the questions that I'm trying to generate as we go along. So what causes this? Well, it's harmonics. We talked about, you've probably talked about this in past webinars. These are multiple frequencies impacting on the current, the fundamental current, to get a distorted resultant current. And as you see on from this this waveform, you can see the fifth and the seventh are very, very dominant in this six pulse arrangements or three-phase rectifier. And if you do an arithmetic sum or RMS to get these together, you will see that it comes out to that resultant red line current. And these fifth and seventh harmonic are very significant. Yeah, they can be, it says 34% on here, but again, coming back to about that line impedance, this could be up to 55% fifth harmonic imposed on that waveform. And of course, the more current what's flowing, the more voltage it's going to generate across the supply. Okay, so if you look at the harmonic spectrum of that, it's based on the pulse number. Again, we see a three-phase bridge earlier on. It's got 6 diodes, 6 pulses of current. And as we go along this presentation, the pulse number is important because it tells you what harmonics will be existing on that distorted current. So in this case, 6 pulse, we're looking at fifth and seventh, fifth and seventh, ninth and 11th, and 13th. 11th and 13th, sorry, I'm getting a little confused myself here, 17th and 19th, and so on. And this is like a diminishing thing. So you can see the currents that they diminish down with the order of harmonic frequency, okay? So as I mentioned earlier, I just added this little slide in. The pulse number is important. The pulse number, the harmonics, what affects on that pulse number, it's just a pulse number plus or minus 1. And it's the multiple of. So in our case, the sixth is a 6 pulse, it's 5th, 7th, 11th and 13th, 17th, 19th, 23rd and 25th, and so on and so forth. As we go beyond the 23rd and 25th, it does sort of get to a negligible value. But again, we're talking large. If we start talking larger and larger powers, it becomes significant. And again, it's not just powers yet of single drives. This could be multiple drives. So we might have 1 megawatts of 100 drives, connected to the system. So we've got to be very aware of this. Okay, so along with this, I just wanted to add in about power factor, displacement factor, because we looked at our original system and it had power factor correction equipment on there. This, just for clarification, there's two sort of like power factors as such. One's detailed as the displacement factor. This is the actual power factor from the voltage, between the voltage and the current, and or the fundamental current, okay? So this is what's usually measured on the utility, okay? So you're only worried about the 60 hertz component because it's the working component. And that's usually around about 0.97, 0.98, okay? It's, we're on that motor now, you've got a driver which is automatically power factor corrected the supply, yeah. But then you've got also the true power factor, which incorporates these harmonics, the 5th and 7th, etc. And it will be, quite less, and it could be down at 0.88. But these are harmonics which you're getting free of charge from Control Techniques, from your other vendors. So they cost nothing when it comes to energy usage, but it will cost when it comes to RMS currents when it's flowing through conductors, etc. So I just wanted to make that clear on that, so we can understand fully now what the impact of those harmonics and the impact of the drive going onto that supply. So now let's have a look at the impact of these harmonics on other equipment and how we can sort of try and prevent some of this stuff happening. So again, there's two distortions we're worried about. The drive itself, as you know, in maybe from ourselves or other vendors, and not just variable speed drives, power supplies, etc. You get current distortion, and the drive, the VFD, is acting like a current generator of harmonics. So it's just pushing these currents out into the supply. And of course, that will increase our RMS currents coming into the system. And that will affect our cable sizes. It could have effect on passive components like reactors and transformers with increased copper losses and iron losses. And then as a result of the current distortion, the supply, the points of common coupling have impedance. And that impedance will see the voltage drop across it generated from this current. And of course, the reactive impedance part of this component will change based on the frequency order, the harmonic frequency. So the amplitude and the frequency becomes very, very relevant. Okay. So we're going to look at a couple of these with a current distortion, two levels, with total harmonic distortion. This is the RMS value of the instantaneous of the current. THD was used a lot in the past, and it still is, and it tells you at any point at load what the harmonic distortion is. THD is as I said, the RMS value, or the summation of all, and I forgot the square root there, and when I've put on there, so it's I5 squared, I7 squared, etc. It's the RMS value of all the harmonics values. And then you've got the TDD, and this is the more important one when coming to specification, because this is the worst case. What's your worst case load of the system? Though I've got a 250 kilowatt pump and drive on there, it might not be drawing that much current. It may be only taking about 180 kilowatts of load at any one time. So you work it out for that. But this is what you need when we start looking at some supply limitations when it comes to IEEE 519, et cetera, et cetera. So the THD, instantaneous values of harmonic distortion, TDD, is the absolute worst case you're going to get on the system, okay? Because the absolute worst case is what people's going to see as voltage distortion on the utility. Okay, again, just to recap then. So if we're looking at current distortion, usually, it's dependent on the impedance again. Typically, it's the RMS will increase to about 12%, 10% to 15% ranges. You can see in sort of comparable conductor sizes and maybe transformer ratings. If I was going to do a dedicated transformer as an isolating transformer for a drive, I would rate that transformer 10 or 20% of its nominal rating without any other things coming into mind. And we'll go into that a bit more deeper on the next couple of slides. But generally, typical values, we're looking at 10 to 15% increase in actual RMS current when this drive is inserted. So here we go, supply transformer. Interesting thing about this is, there's a lot of copper in there and iron. And of course, there's three lots of losses what could be considered. The resistance losses, and again, the frequency is the key here because the harmonic is, as multiple as the fundamental. So with the skin effect, this can increase, at the square root. The hysteresis losses is proportional to harmonic frequency, and then the increases with the square of the frequency. So these have an impact based on your THD and the harmonics you've got present in your system. So today, when you rate a transformer manufacturers you should be very visible with them when you're supplying the transformer and say, like, I've got it's a nonlinear load, high THD. This is a THD factor, and they will rate the drive with a K factor to help with the size in this transformer. And typically, the K factor on a high THD system, the K factor is around about 13. Okay. With the generator, being NEDEC, Control Techniques, we have 2 generator arms within our company, Cato Engineering and Leroy Summer. Leroy Summer is more European-based. Cato, as you know, is US-based. These guys do some really large generators, and not just low voltage, but MV. And they use this the derating curve for harmonics. Anything with more than 10% THD of current, then it will have an impact on the minimum rating of the generator, okay, from a thermal capability, correct? So Cato, in this case, this is their derate curve. This is a typical salient pole wound field synchronous machines. This is what they use. And I guess every manufacturer will have something similar based on the type of machine of generator you use in a PM machine or a fully induction machine. So this is just purely looking at, copper losses with the current total harmonic distortion. So again, if we looked at typically the drive, 6-pulse drive, and we had 50% THD, we're looking at, sort of an 87% derate on the actual generator. Okay, so some simple guidelines. Again, this is the kind of thing you consult the generator manufacturer to, and again, some detail on why. Okay, these things, and of course, most of the machines like transformers and generators have been designed for the 60 hertz. Yeah, and when you start getting harmonics, they have to go somewhere. So they have to accommodate that within the machine itself with the losses. Okay, so I'm going to move on to voltage distortion. To me, this is the big one people should be aware of. But the challenge is getting the information to be aware of what this voltage distortion result would be. Skews the eyes, but again, if I look at a point of common coupling on low voltage, when you get voltage distortion, everything in that system will see that voltage distortion on the supply, of course. The voltage distortion is a product of the supply impedance, okay? Of course, there's some resistance in there, but it's negligible compared to what the reactance could be when it comes to the inductance. As you know, with a transformer or generator, there is impedance purely for fault level conditions. With the transformer, we're talking percentage impedance, and then with the generator, we've got subtransient reactance. So that current gets generated, we get a resultant voltage distortion across the supply impedance, and then that gets reflected across all the loads. And of course, getting it too high, it can impact and influence other loads on the system. So I'll put a little single line diagram, line to neutral, just to depict this. Yeah, there's cable impedance, usually negligible, but most of the impedance is in that transformer, yeah, or the generator. Again, not just really focusing on VFDs, but it could be UPSs, etc., on large systems. Again, transformers, percentage Z, or the fault level, either one, you can determine what the inductance is. The generator is usually stated as subtransient reactance. But the important thing to note here, and this is a differentiator when we look at generators, is the subtransient reactance is probably 3 to 5 times greater than the equivalent transformer. So you can see that if simple Ohm's law really, yeah, if I got 3 to 5 times more impedance there, I got 3 to 5 times more voltage distortion potentially on a generator when it's connected. So this is an area I would seriously sort of consider when we start thinking about generators, but what levels do we need to really be considered with, and that's going to be the next question, yeah. But again, the generator, depending on how critical the job is, etc., those parameters can change. You can get lower subtransient reactance designed in, but at an effect of the performance of the generator changing. Okay, so it hasn't been known to get lower percentage or subtransient reactance values, but again, something has to give on the generator to get there. Okay, so just a quick overview. If you look at the two, you know, we've got transformer and generator, we've got percentage impedance and subtransient reactance. Typical values of percentage impedance for the transformer, 4 to 6% is not unusual, between 0.5 megawatts and 2.5, sorry, MVA. And then typically on a subtransient equivalent, subtransient reactance on a generator could be between 10 and 20%. Typically, it can go up to 30. You know, which is interesting. But again, it's important to understand, you know, that impedance is significantly higher. Again, another little application. I'll talk about regeneration. When we start thinking about drives and regenerating power, yeah, we could use a brake resistor for regeneration power, but we could also use a regen or an active front end to do the regenerative power. Got to be very, very careful with a generator, yeah. We've got to look at the limitations of the mechanical driving force, usually as a motor engine or hydro, etc. Can you actually regen back? And you typically, rule of thumb for myself is usually 10 to 20%. You can dissipate back into the generator before you start pushing the volts up. Again, it all depends how that can be overhauled from a mechanical standpoint more than the electrical generator itself. Another important point with a generator, and I don't know if it's so relevant today, but the AVR is important because now we're talking about nonlinear loads. The AVR used to be an average, use average voltage, but now if you use RMS voltage with nonlinear loads, it's more robust. You get the accurate figures of what's being produced from the generator. And from that RMS value, again, we'll talk about it a bit more about later, we can adjust to suit the conditions based on the distortion of the voltage. Okay. So again, just a little picture really, just to emphasize that generator reactive voltage drop. It's significant. And again, if you don't rate these generators right, you can have all sorts of problems with the distortion and also, you know, affecting other equipment, which is when you know you've got a problem. Yeah. The drive is pretty resilient to the distorted voltage, but the generator may not be based on the AVR and how it controls it. And as soon as you get something else on the equipment, it gets affected, then it's an even bigger problem, yeah? Especially if you're connected on the same supply as the adjoining office or a domestic line at MB, and people's having problems with lighting, TVs, etc., then it's even more of a significant problem. So it's important that we try to identify these issues before we start putting the project together. Okay, so voltage distortion. I'll put some equations up here, very, very straightforward, simple equations. You can go to the nth degree on these, but how to derive the impedance of the generator or the transformer, same math applies really. It all depends what parameters you have available to you. But again, that voltage distortion, if we move to the right-hand side, it's all down to that impedance and the frequency we're operating with the amplitude. Again, that makes a significant change to the voltage distortion, and then they are all RMS together to give you the total THD. So just a reference point, really. Most of it should be very straightforward on the left-hand side for you guys managing with power. But then when it comes to the frequency side, it's just a case of substituting the harmonic number in there to try and drive the THD. Now, again, I've done this for many years in my past, from pen and paper to now an Excel spreadsheet. So it's a bit more automated, provided you can get the information. And this is the challenge here with voltage distortion, is if you don't know what you're connecting to, it can be a problem. But again, if it's a critical site, especially downtown areas, you can take a place like New York, London, etc. They're going to have very high levels of distortion anyway. So they've got a challenge to keep the distortion levels down. usually that you should get more information available to you, because again, I'm trying to minimize or eliminate the existing harmonic levels, or not increase them, because from your TV sets, etc., it all adds into this this larger scale harmonic distortion on the grid. So again, we'll talk a bit more about how we can minimize that later. But to me, the voltage distortion is most important. Yeah, current distortion is a product of, but if we can control the impedance of the supply, we're in a better position. So I put a little bit on the power factor correction here, because we got it on our system there. Again, don't forget this guy. Okay, you just put a drive on the system. Is the power factor correction on your plant, sir? Yes. As it is, can we look? Is it a potential resonant path for it to resonate these harmonic frequency? So, of course, the first thing you should be taking care of is, like, what's the existing power factor correction in there? What's it trying to correct as power factor? Do we need it all of this now? Has it got automatic PFC relay switching? If it has, it's the better. But it's very important that we don't go leading power factor. Now we put more of a better load on here with a better power factor. But the resonant thing is the key here. And again, these do crop up still today on existing systems, where the actual supply is tuned with a capacitance, and it gives you a short path to burning capacitors out or blowing fuses randomly, okay, when equipment comes on. So there's ways you can get around this. Either take the capacitor out, which probably a lot of people do, or you can detune it away from any of those frequencies. And there's a method. Again, you can challenge yourself. You can do it, but your power factor correction capacitor people or your filter people will be able to help you analyze what reactor needs to go in there. And usually they set up a tuning frequency to like an interharmonic type value, which the fifth harmonic, 300 hertz, they might decide to tune it at 275 hertz or something like that, which is never going to get there, or even a higher frequency. So it tunes it away, keeps the capacitor doing its job with the 60 hertz component, and keeping the reliability of the system up. Okay, another thing what could come up is, those capacitors coming switching on. I talk about auto switching. There is tendency that they can surge now and again. Again, the reactor may help. Input line reactor to the drive could help as well, with that sort of scenario. So just be aware of this PFC. It's an important point when, especially on larger drive systems where you're going into a plant. Okay, so what's there to help us try to minimize these harmonics? There's IEEE 519 in the US. There's two versions, the 1981, which was mainly based on the voltage distortion for common coupling. And then 2014, they brought it out with the limits of current distortion. Okay, so current distortion has been used a lot. And of course, that makes sure that the vendor, if you don't know what your supply capacity is and whatever, the vendor ensures his current are down to a minimum to make sure that the resultant voltage distortion is kept down at the same point. So we talk about that. Current distortion is very, very critical. Yeah. So if you have a 519 challenge with current distortion, usually we have to adopt a different method of harmonic reduction. And we'll talk about that a bit later. But with voltage distortion, you've got a chance, yeah, but you've got to know the supply. And this is why they brought the 214 out, because not a lot of people know what it was connecting to. And it's always a challenge for some people who's mass producing systems to go in pumps or fans, etc. They don't know where it's going, especially on larger powers or larger drive systems. Okay, so moving along, this is the 519 for current distortion. Some of you may be already familiar with this. What's the indicators to use this guide? Of course, the thing what gives it away for me straight away is this short circuit ratio, which gives you an idea what the supply impedance you're trying to challenge with. Okay, so the short circuit and load impedance gives you an idea if you got a certain load, the short circuit ratio, you should be able to, you've got to limit each individual harmonic amplitude to these values, and then your total demand, i.e. THD at the demanded load or the maximum load cannot exceed this value. And it's a challenge when you start thinking about maybe 100 horsepower and above. In some cases, okay, it may be even lower. It depends on that size of that supply. Again, if we put in perspective, if I had a 1 horsepower drive and a 1 MVA drive, though it's got 56% fifth harmonic, it will never generate the distortion on the supply of 5% or etc. or more. So it's a very ambiguous sort of challenge, shall we say, but it can be handled in the right way. And ultimately, if the customer wants table 2 harmonic, you got to supply a solution. But if you've got a more openness of 519, then I would lean more to the voltage distortion, because you have to get the more information about the network, the supply you're going in, because again, it's a large capital investment to get the harmonics down with the current without knowing where it's going to. So if you know where it's going to, you could probably be very competitive on price, okay, with a more an expertise solution. And again, I understand this is not already ready available to everybody when it comes to supply information. But again, if you can get it, it might take you that step further to succeed in that project. So with a transformer, again, I took this solution with what I started off with. Excuse me. So when we're looking at transformers, what do we need to do? Of course, typically we derate by 20%. Okay. Then we got the power factor. We detune the power factor stuff. And then does it have to meet 519? So then we need to review where is the point of common coupling, because it may not be on your low voltage side, it may be on your medium voltage side or high voltage side. So you got to calculate it through. But again, if it's current, then it's got to be reduced at source. Okay, there's no getting around it, and of course we've got to use different techniques to do that. And I've got this at the end of the slide at this presentation. So I took that 250 kilowatt 6-pulse drive, we put on that 1 MVA transformer, and ran the math on it. We have data sheets for all our products for the total TDD, the worst case harmonic generation. And of course, you're looking at, RMS currents of 484 amps and the fundamentals 429. And of course, we've got about 45–50% fifth harmonic. So, we would never meet the table 2 on 519. But when you look at the resultant voltage distortion, it's well within what's publicized in the voltage distortion guide. So again, that would run satisfactorily, no issues. It all depends if we've got to meet that THD of the current. Okay, so with a generator, what do we need to look out for? That THD is important, so we derate to the THD. That's our first step. The second thing is making sure that the AVR is true RMS. And then coming back to that point of common coupling, most of it will be one. There's no grid in this case. We just got one supplier, of course. Yeah. What have we got to look at? And of course, in our existing diagram, we have a connection at low voltage, and we got 2 to 3 times higher of transformer. Of impedance. So the generator is going to struggle. Yeah. Just basically on that subtransient reactance. Of course, we've got a 1 MVA generator. It's a lot larger than our load, we hope, based on the other point of common coupling devices. What do we need to do? And of course, we'd have to upgrade the transformer, yeah, to get the same voltage distortion level. So we'd have to upgrade the the generator, not the transformer, by a factor of 3. So we've got the same voltage distortion level. Okay, because we've got a 15% subtransient reactance compared to a transformer. So it's like a 3-to-1 ratio. So a simple rule of thumb, you just upgrade it by a factor of 3, which seems a very large investment to do, But if we had to meet those levels, that's the kind of thing we might have to sacrifice to do, yeah. So again, this will meet the voltage distortion, but not the current distortion at the point of common current, which is the low voltage point here, okay? All right, I understand I'm running out a bit of time, so I'm accelerating along. Again, with the generator, just another things to consider, you know, that flat topping is important, you know, it's gonna get affected if you've got large induction. So for example, you have 2-to-1 ratio generator, you're gonna get a very, very high voltage distortion. Nothing else connected to it, you may be okay. If the AVR can control it, we're good. Can we provide the volts now? Because we've got flat topping and we're not seeing the right voltage coming through on the DC bus, which in turn gives us our voltage to the motor. So in some cases, we may want to turn up the AVR a bit higher to its maximum rate of the drive so we can get the volts through so we can produce the right amount of torque on the motor. So again, you know, you can see, get a feel for this subtransient reactance. It is important to see how we can minimize it, or how can we reduce the harmonic currents at source. Okay, now voltage distortion on SCR-based drives, I said I wasn't going to talk about this, DC drives, etc. You could have some challenges, okay, because the notching effects and the synchronization could have some problems. And again, especially with DC drives with very light loads, it can be instability. So I just put some little extra notes in there just as a guideline for some of these things when considering with generators. So again, I'll give you the overview of the supplies now and things on the supply. How can we try, instead of increasing the supply, can we get rid of some of these harmonics with some harmonic reduction? And again, hopefully some of you know about this, but I'm just going to give my thoughts on this and what we supply for control techniques. Of course, first thing people think about is impedance. You know, if I put more impedance in there, can I reduce these peak currents? Well, you can, but there's a point where you cannot reduce any more. Okay, and from experience, 8% is a very large impedance to put on the front end of a drive, but it would reduce the currents down to around about 35% currents, and that's it before you start affecting the performance of the motor, because now you're starting to starve it with volts. Okay, so that input impedance, it's balanced in a way to make sure you've got good reduced peaks, but also ensuring you can still flux the motor with the right voltage on the terminals. So we can do this as an option, but again, case by case, it may be not used based on if I need full torque, full load, full torque at full speed. So these are the kind of things that needs to be balanced out. Classically, which is used a lot, 12, 18 pulse transformers are pretty common. These are great. They work really well, especially if they're on a common core, not separated. Nice balance of distribution of the currents. There are ways you can do this with auto-wound transformers. It's just trying to find that manufacturer in the right cost point to do that, but not to the same performance as an isolation or double wound transformer like shown on this diagram today. Has very good performance. You can see now I've gone from a 6-pulse drive to a 12-pulse drive. So now I eliminate or minimize my 5th and 7th harmonic. And all that's apparent now is the 11th and 13th and 23rd and 25th and so on for the 18th pulse. So here's some graphics to just show you how the current waveform gets manipulated based on the cancellation of the 5th and the 7th, and of course it brings the THD down significantly. So this, a graphic, with the phase shift, we talk about 12 pulse. What do we need for a phase shift? It's a very simple equation, 360 divided by the pulse number. Tells you what the phase shift you need. The beauty about the 12 pulse, most manufacturers can provide that transformer. It's a star delta configuration. A star delta winding has a natural 30 degrees phase shift between the windings. So pretty conventional, been with us for a long time. Again, now we're starting to look at zigzag type of arrangements to do more like 18 pulse or 24 pulse, and there are also auto wound transformer solutions as well. Okay. So this takes the THD down to about 12 to 15% if we were realistic with ourselves. It doesn't eliminate the 5th harmonic completely due to imperfections of of the design of the balancing between the supply and the transformer windings and the accuracy and tolerances. So you get it down significantly. So it's, you know, a couple of % or more. But again, you can see the big difference in the wave shape alone without even looking at the harmonic spectrum, correct? So there's the double peaks are gone. We've got a bit of a sort of a woody look on the 12 pulse. And again, same on for the 18 pulse with dog-legged secondaries, 18 pulse, more rectifiers, maybe a bit more complicated transformer maybe, but it's achievable. Again, auto wound or double wound transformers. And again, you can see that now your total THD is coming down to like 5%. You know, you're getting into that realm now where it can meet the IEEE 519 for current distortion. And you know, just graphically looking at it, it makes sense. Yeah, the more pulse number you go up, the smoother the current gets. Again, this comes at a price, of course, but also with a form factor. Yeah, transformers are not small, and as we start going above those 100 horsepower sizes and above, they get quite large. So people start thinking about putting that transformer as an outside transformer, you know, oil filled, etc., just to alleviate the transportation of this thing inside a cabinet, etc. So, you know, that's a couple of things you've got to be careful on is the size of these things, okay? But they work really, really well, and they've got a high success rate. There's little that can go wrong with it because it's just a transformer, okay, and some extra diode bridges. And then we've got the active front end. Sometimes we call this our regen front end. This is a very high performance drive. It's just basically with control techniques, we just put drives back to back and change the mode, and then add some additional filtration components on the output or the input to the drive, with a couple of reactors and a capacitor. This has a far superior performance compared to the 18 pulse, and the price point is very attractive as well compared to an 18 pulse. It's fully regenerative. The other good thing about it, it has a controllable power factor. So unity is the default, but you can put leading and lagging VARs on there if you needed to, just to correct the supply. But again, if you are looking to do that correction, of course, you've got to remember the resultant size of the drive is going to be bigger, okay? Because now you're trying to provide VARs to the system. And as I said, this is a standard product from Control Techniques, along with some additional external filtering components. The right-hand side, it gives you an idea of the PWM waveform and how that filtering component sort of smooths out everything. And again, typically 3 to 5% harmonic ITHD. We've used this in many different applications, not just pumps, but high dynamic applications where you want high speed regeneration. Okay, so basically it's just going over what I explained, but with a schematic diagram. So you've got a clearer view of what's going on. The transformer is not part of the package, it's just showing the isolation transformer. But again, because it's a PWM output, we put an EMC filter on there if needed. It is optional. It's not that it does a crazy, whether everything's going to go crazy. No, it's just to meet the EN norm of Europe while the EMC filter has been put in there. Okay. So moving on, active front ends is typical performances. So again, just so you can compare it to the die rectifier, yeah, you pay more for it. It's comparable to an 18 pulse solution as cost, but the performance of reducing that THD, now you can start thinking, oh, I don't have to put my generator to 3 MVA, you know, can I bring it down? Okay. And then the harmonic filters, and I think some of you guys have already had some experience with passive harmonic filters. Again, you can meet the IEEE 519 easy with these things. They are very compact compared to a equivalent 12 pulse, 18 pulse transformer. But, you know, you need to be aware and be careful on, again, how you apply these guys. Again, it's a capacitive passive filter, so you have a tendency on lighter loads to go lead in power factor. That's why the contactor's in there to switch it out when the power factor goes lead in. Some people don't even see it because they've got big lagging bars on the system already, so it doesn't come up that often. but also just be aware of background harmonics. Okay, it is a filter. So if you've got background harmonics, meaning something coming from somewhere else, it may have a tendency to absorb some of that. So it's for a solution, it's perfect. It's good cost, compact. Just be aware of some of these things on here, because again, it is a passive component. If you don't know where it's going, sometimes you could have some challenges. Okay. All right, so I just did give an overview, so hopefully I'm doing well in time, maybe a little bit over, but just a little overview on my view on things, and you know, from a THD and those 5 solutions, and you know, the AFE and filter are the most attractive, of course. From a weight side of thing, when it comes to cost, the AFE is pretty comparable to the 18 pulse, if not cheaper. Filter is probably the lowest cost solution. Of course, the 6 pulse is the reference point, so it's going to have the green light, of course. But yeah, just a general overview. But again, lower harmonics comes at a cost. Yeah, there's no doubt about that. If you got an existing system which is very large, you probably won't even need to do anything. Smaller drives, the better. When it comes to harmonics, though, they've still got the same percentage. Though it's not having that much of an impact on the supply. If it does, you know, large powers, I said 150. I've seen them lower at 55 kilowatts and above. What's that, 70, 60 horsepower above, going 12 pulse too, to make sure they meet the IEEE 15519. Again, it depends on number. Again, it's not just a singular, but a number of drives up smaller. I think the filter is a good solution for a generator. Again, it's compact, it's easy to put in there. You can take a standard drive, little hassle. It's a part number, and most drive manufacturers will supply that solution. Okay, and then again, other things to consider when you have multi-drive solutions. Why not consider a common DC bus with a common sharing power, and also maybe less impact to the supply. Again, we've done quite a few of these systems with partners and our NIS team, which has been very, very fruitful, because again, you're not pulling anything from the supply. It's all on the common DC bus, and then you can put an AFE on their front end to supply that motor power and regen power if needed. So going back to our original diagram, what have I done? Well, I've changed the AFE to a different type now to have a minimum impact on the supply. I've used a filter or an AFE here, and my generator, you know, a rule of thumb, you know, though it's 1 mega MVR, I've gone up by another 50% just to be on the safe side. So I have no nuisance voltage distortions, and again, I'm not too reliant on that subtransient reactance. Maybe it's not 15%, maybe it's 25%. So I just put a small D rate on top of that. The capacitor is still detuned, because you never know. It only takes something to come in and it takes it away. But the overall thing, the impact on the system is minimal now. It's less than 5% THD current harmonics for that table 2 on the 519. But again, if we went back to a couple of things, if you're operating around at 4 to 6% VTHD, voltage harmonic distortion, you should be good. You should be good. I'd be very surprised if you have any impact on other equipment. When we start getting above that, and you start seeing the distortion of the voltage wave, then you know something's you're going to be exposed to some threat somewhere from some complaint. So that's sort of concluding today. Again, when it comes to harmonics, I've always been brought up to say, if you've got a harmonic problem, minimize that source. And your source is your drive. What can we do to get the harmonic mitigation down? Of course, that's what the idea of the table 2 was all about on 519. Control techniques can provide a numerous solutions for doing this with filter, AFE, and multi-pulse solutions. But again, if that's not the case, if you can't do that, how do you make sure your supply capacity can cater with the increase of these harmonics? Okay.
Great. We do have a couple of questions that have come in.
Okay.
Feel free to continue to submit questions while we're answering these. We'll start with the most recent one. If you have an existing VFD system how can you tweak that system if you are about to install a standby generator into it to ensure you don't cause problems for the generator?
Okay, so again, tweak the system. I use the word. Someone's using my word from yesterday. I think. but yeah, tweak the system. Probably the easiest way is just make sure, if you, there's a couple of ways. If you can get to the system and it's existing, you can measure the voltage distortion, what's already on there, or get the impedance of the supply. And from that, you can make the relevant calculations for the generator. The easiest solution would probably be, can I upsize the generator, or can I put an input filter without having a large impact of the existing VFD? Because if we've got to put an AFE on the front end of it, you can put an AFE front end to it, but it's costly, time consuming. But I think your easiest route would be to say, first of all, what impact is the generator going to have on the supply compared to what I got today? If it's going to have a large impact, it's going to go over that 5, 6, 7% THC. A filter is probably your best route forward, especially for a generator. Now, in an existing installation where they've got current problems with transformer, with distortion, where they may have 2 supplies, 2 transformers feeding a constant running machine. Then on the point of comes at MV is interfering with a residential estate, etc. You could change the transformer configuration and do a pseudo 24 pulse on the supply transformer, and not touch the drives. Okay, so there's different ways of engineering a solution on a power supply.
Next question we've got: does anything that you've discussed on the generator side change if you're using the generator for prime power compared to standby?
Can you repeat that again? Sorry.
Yeah. Does anything you've discussed change if you're using the generator for your prime power as compared to using a generator for standby?
I would treat them both the same because it's continuous running, and the beauty about the generator in some respects is you've got no MV, got no primary side. What you got is local point of common coupling. The beauty about that, what I'm trying to say, the beauty of, is the owner of the LV is your customer, the site. If he has high distortion and it doesn't meet IEEE 519, but everything runs satisfactorily, he does not need to change anything. Okay, and you find this a lot in the steel mills and whatever, because their system's immune, it works okay. But if you're worried about what's the difference between a standby generator and a continuous generator, both rules apply, because the standby generator may be running continuous for days, as backup on a municipality. So.
If you are running off a paralleled generator system, are there any additional concerns with VFDs?
So yes, one of the things, if I remember on parallel generators, which I've done semiconductor about, is when you synchronize generators in and out, making sure that the synchronizer is picking up can synchronize that distorted waveform. Again, if it's too distorted, they may have trouble synchronizing the generators in and out. Okay. Again, it depends on the synchronizer for bringing that generator in and out. Of course, if you've got 2 generators acting for one big power supply, of course you've got half the impedance now, total impedance. So the THD should drop down for the same load. But if I was thinking about a generator with two generators coming on duty standby or both together, the synchronizer would be the one I'd be worried about to make sure we got good synchronization when the generator switched in.
Okay. As far as remedial techniques, how would an active harmonic filter compare to the other?
Yeah, so an active is a good question. Active, I've not been really involved with active filters. Control techniques do not make one today, but I can see it as an added benefit, because you can just plug something onto a current system, okay, and generate harmonics back onto the system, which is anti-phase to what's already on there, and be an active filter. It should be dynamic, yeah. So as these filter, as these harmonics increase or decrease, the filter tunes into them. Now, how we size that thing, it depends on how much THD is already on there, okay? But it's a good question, and it's a good technology as well, don't get me wrong, where it's an easy plug-in without disrupting the system too dramatically. Again, reliability, availability, I can't answer those questions. So
it looks like I know our conversation today is focused on VFDs, but we got a question. Do you see similar harmonic issues with soft starters?
Soft starters. Now, if I had to categorize a soft starter, I will put it in the DC drives in area, because when it starts ramping up, when the soft starter's in, you will probably see some notching effects coming on. And the thing about a soft starter and a DC drive, it's more like a current source, and you'll probably see more of a squarer current than like we see on the voltage source. But you're only worried about when it's starting up. And I can stand corrected here, because it's such a short time when it happens, it can impact equipment, and it could have a problem. Because it's a short time, it's catching it to make it see that it's affecting the equipment. So it depends on how often that soft starter comes on and off. I think it can be disruptive, just like a DC drive. The DC drive, the current harmonics on a DC drive is lower, but the biggest challenge with a DC drive, because the thyristor commutation, is the notching effect.
It looks like someone's talking about where your slides pointed out that the point of common coupling is typically the low voltage side of the supply transformer. In what cases would it not be that location?
If you're connected, so if I'm a steel industry connected right next door to a suburban community, the point of common coupling would be that taking up the MB. If you're disrupting, you've got a chance of disrupting that community. So you've got to be very careful the point of common coupling. The point of common coupling maybe for a sort of building, a high-rise building, where they have HVAC drives on there and all that. The point of common coupling most likely is going to be LV, because you're interrupting with different departments on that same power supply. But again, what happens if you're a big industrial unit making steel or paper? Your PCC internally may be important for you, because you're the only person on that low voltage. But if you're interfering with a local community or another customer, another industry or another factory, then the point of common coupling may be, well, most likely be MV.
Can harmonics cause actual physical failures in a generator, or is it only going to be performance failures? If it can cause physical failures, what parts of a generator are most likely to fail?
And again, I'm not a generator expert. It's the only one I've learned. If you didn't derate the generator, it's got more likely to be the rotor, which it didn't fail, the heat in the rotor, and I stand corrected on that. But if you didn't derate that, say you had 50% THD and didn't derate, I got a funny thing, you start seeing things burn out and get hot.
Okay. It looks like that's all the questions we had come in. So again, we'd like to thank Kevin Manton today for joining us from Control Techniques. We'd like to thank all of you for joining us. We will be sending out a recording of this webinar, but otherwise we'd like to thank all of you for joining us today, and we look forward to seeing you next time.
Thank you.